Well, let's start our lecture on hypersonic dynamics. Today we have lecture number 13, non-similar hypersonic boundary layer. Now, prior to 1960, the everyday work of boundary layer application emphasized approximate solution of the boundary layer equation. Many of the approximate solutions involve the assumption of polynomial profiles for U and H across the boundary layer, and the application of the integral forms of the governing equation. Such integral solutions of the boundary layer are well known and extensively presented elsewhere, and hence they will not be considered here in our lecture. In the modern world of hypersonic aerodynamics today, exact solution of the boundary layer equation can be obtained numerically for arbitrary pressure, and means hence velocity, okay? Radiance external to the boundary layer. And here the word exact is being used in the same computational fluid dynamics sense. That is, the exact boundary layer equations are used, but errors are introduced via the numerical solution in the form of truncation and round-off error. And hence, we can readily state that the numerical solution of arbitrary non-similar boundary layer is fairly common practice in hypersonic aerodynamics today. Yeah, it's true. The purpose of the present module of our lecture is to provide the flavor of such non-similar solutions. The existing literature in this field is so expansive that we can only highlight some of the more important developments. In this lecture, we will introduce three separate methods for solving general non-similar boundary layers: local similarity, differential approach, and finite difference solution. The first two are somewhat historical in the sense that they are no longer in widespread use today, but they constitute interesting ideas with which any of you, and generally saying any specialist who studied hypersonic viscous flows, should be acquainted. The last item, finite difference solution, represents today's state of the art. And finally, in regard to the model of a roadmap in this slide, we are now temporarily at the bottom of the map. That is the last of the items shown under the box at the left side of the map, labeled the laminar flow boundary layer equation. Okay? So the first topic, the first question of today's lecture, local similarity method. The method of local similarity is not a precisely exact solution for general non-similar boundary layers, but it is an important bridge between the exact self-similar technique and the exact non-similar solution in the present model. The concept of local similarity is outlined now. First, consider a boundary layer with properties at the outer edge and at the word that have an arbitrary variation with x as sketched in this figure. Second, apply the general transform boundary layer equation to a small slice of the boundary layer located at some local value of x, say x equal x1, and this small slice is shown as the shaded region located at the x1 in this slide. Take the thickness of this slice delta x to be small enough such that the variation of tw and u sub e and a sub e, b sub e, etc. over the delta x. So it must be small, right? And then, indeed, assume that t, u, h, etc. to be equal to the local values, namely at the x1. And this includes the gradient du over d zeta, which is taken to be a numerical values in this equation. Yes, you see, equal to its local value at xy. Third, in this equation, assume that all the partial derivatives with respect to zeta are namely df stretch over d zeta, df over d zeta, and dg over d zeta are small and can be even neglected. This is why the local similarity method is an approximate method. In a truly self-similar solution, these derivatives are precisely zero. Here, they are finite, but we assume them to be small enough so that they can be neglected. Okay? And four, under these assumptions, our equation becomes to the upper one. And after that, we may transform on the second one of the middle of this slide. Whereas these both equations are approximate form. At any given x or zeta station, du over d zeta, rho, u, and h are the local values. And hence, enter our equations as specific numerical values. In contrast, these equations will be seen as the ordinary differential equation. And hence, these ordinary differential equations can be solved, say, by the shooting technique described earlier. I hope you remember this. Okay? So, at the local value of x, the solution gives us the f from eta and g from eta for the slice of the boundary layer located at x1, the first shaded region here. Okay? And 5, next, pick another slice of the boundary layer at another value, say x equal x2, and repeat the preceding process. This is shown schematically in this part of the slide, where two locations are denoted by x1 and x2. The preceding locally similar solution is carried out at each value of f, resulting in f1 from eta and g1 from eta, and the same f2 from eta and g2 from eta. In general, we have non-equal equivalence between f1 and f2, the same as non-equal equality for g1 and g2. And thus, the local similar solution is a solution of the non-similar boundary layer, albeit in an approximate sense. And final six, after application to many values of f, the preceding procedures yield the skin friction via the second derivation from f equals 0 and heat transfer as function of f numerical. Okay? One of the best examples of the application of local similarity is the work by Kemp, which treated by the boundary layer over a hemisphere cylinder as sketched at the top of this figure here. This work treated chemical reaction, dissociating air, which is the purview of these lectures part in the first part. However, these results are presented here to demonstrate the viability of the local similarity method. Figure on this slide gives the variations of Q as a function of angular distance psi away from the stagnation point, as measured in a shock tube. The free-stream conditions were such as to simulate the pressure and the enthalpy level associated with the free flight in the atmosphere with the velocity of 18,000 feet per second at altitude of 70,000 feet. The actual shock tube free-stream conditions were different than the preceding velocity and altitude. Recall, only low supersonic Mach numbers can be produced in a shock tube, but the actual stagnation enthalpy and pressure can be directly simulated. These symbols in this figure denote the shock tube data, and the curve represents the local similarity calculation. Considering the scatter of the shock tube data, the local similarity method compared well with the experiment. And the numerical results indicate that for ordinary blunt body, the calculated variations of G stretch from 0 as a function of x around the body is very big. To be precise, for the conditions we have between nearly 1 exactly, higher than 0.96 and less than 1 also. That is, the transfer enthalpy gradient at the wall is essentially the same at all points around the body. And then the strong variation of Q with angle psi shown in this figure is caused by the variation of the H, rho, and U in the equation. And you should note that the local similarity method blocks out any effect of the upstream properties within the boundary layer. The calculation at any given x does not utilize value of the boundary layer profiles upstream of f. And therefore, the history of the development of the boundary layer from the leading edge to the local station is not properly accounted for in the local similarity method. However, the upstream history of the inviscid flow is transmitted to the local similarity solution, as the local values of U, H, etc. are influenced by the history. This physical defect does not appear to be serious, probably for the following reason. The boundary layer equations are parabolic partial differential equations. For such sort of equation, information is readily transmitted across the flow, normal to the surface. At the same time, information is carried downstream. However, the history of this information dumps out quickly with distance downstream. That is to say, the real physical boundary layer at any given location X is mainly dominated by the local wall and edge conditions at X, and so these conditions are the driving parameters in the local similarity method. Okay? Our next questions of today's lecture: differential method. Unlike the approximate local similarity method just discussed, the differential method is inherently an exact solution of the general boundary layer equation. The general idea was originated in 1937 by the Hartley and Wormsley, but was not applied in a practical sense until the work of the Smith in 1960. Smith utilized the differential method extensively, and the idea is as follows. Consider the general transform boundary layer equation. These equations are to be solved for arbitrary flow conditions at the boundary layer edge and the arbitrary wall condition. This arbitrary boundary layer is sketched in our figure on this slide. Also shown is a grid network as the 4 different zeta or X stations, namely I minus 2, I minus 1, I, and I plus 1. Assume that we wish to calculate the boundary layer profile at the station denoted by I. Okay? In the differential method, the zeta derivatives is 2 equations are replaced by finite difference quantity. For second order accuracy, Smith used the following 3-point one-sided difference, as you can see here on the middle, at a given J. Identical expressions are used for df stretch over d zeta and dg over d zeta 2, as you can see here on the bottom of this slide. We assume that the boundary layer profiles have already been solved at location at near the var I minus 1 and the more earlier I minus 2, and hence the function from I minus 1 and I1 minus 2 are known numbers. The only unknown is only f from I. Okay? And hence, ordinary differential equation can then be integrated across the boundary layer at station I in the same manner as described a bit earlier. That is, using an iterative shooting technique to match the boundary condition at the ball and the outer edge. But you should know that equations are still the exact boundary layer equation. No simplifying physical assumptions have been made in going from this equation. Therefore, the differential method is an exact method for the solution of general, non-similar boundary layers. Returning to our figure, and recall that the solution at location I is dependent on previous solution upstream of I, namely at I minus 1, I minus 2, the entire boundary layer solution must be started at some location, say a leading edge or at a stagnation point. Okay? In this figure, station 1, as you can see, is denoted, namely that stagnation point. The boundary layer solution at this location can be obtained from the self-similar solution discussed as several lectures ago. Moving to the next downstream location, namely stagnation point 2, the differential method can be implemented, but with 2-point one-sided differences for the zeta derivative, as you can see here on this plot. Moving to the next downstream location, station 3, right? The full method, as just described, can now be implemented. In this fashion, the complete non-similar boundary layer over the whole body can be calculated. As Smith and Clutter state, meeting boundary conditions efficiently has been the most difficult part of the entire problem. But nevertheless, the differential method is an exact solution to general, non-similar boundary layers, and it has been applied with success to hypersonic problems. An example is given by this figure on the middle of the slide, which shows the heat transfer distribution over a flat face cylinder at Mach numbers between 7.4 up to 9.6. The open symbols represent experimental data, and the dashed line is from the local similarity method, and the solid curve is from the differential method. But you should note that, as it to be expected, the differential method gives better agreement with experiment than with the local similarity. The flow over a flat face cylinder is a good test case for any theory because of the boundary layer is highly non-similar, especially in the rapid expansion region at the corner. Note also the physical trends shown in this figure. Here is a case where the stagnation point is not the location of maximum heating. Rather, the peak heat transfer occurs in the corner region. The physical explanation for this is as follows. The rapid explanation of the inviscid flow around the corner imposes an extremely large favorable pressure gradient on the boundary layer, which results in an actual reduction of the boundary layer thickness. In turn, the temperature gradient within the boundary layer, including at the bore, are increased because they are inversely proportional to the boundary layer thickness. So what I may say, we have differential dt over dy is the omicron over t over delta, because the q is we therefore expect the local heat transfer to increase. And this trend is clearly demonstrated in our figure. Okay? So you can see here, namely, one of the peaks. Okay? Next question of the topic of this lecture, finite difference method. In the differential method recently discussed, the zeta derivatives are replaced by finite differences. The next logical step is to replace both the zeta and eta derivatives by finite differences. Okay, I agree with you. And such finite difference solutions will be discussed here in this part of our lecture. They represent the current state of the art in the hypersonic boundary layer solution. So, assume that we wish to calculate the boundary layer at station I+1, here in this one, as you can see, and the general philosophy of finite difference approaches is to evaluate the governing partial differential equation at the given grid point by replacing the derivative by finite difference quotient at that point. So consider, for example, the grid point I and j, okay? And at this point, replace the derivatives by finite difference expression of the form of the top here. And then we have next two for eta and eta squared. F, we will be changed according to this simple expression, okay? Here we have the theta. This is a parameter that adjusted to various finite difference approaches. More detail will be discussed next. Similar relation for the derivatives of g are employed. So when these three equations are inserted into two previous parts we just recently mentioned, along with the analogous expression for g, we get two algebraic equations obtained. And if theta equals 0, the only unknowns that appear are f sub I plus 1 and g from I plus 1 and j, which can be obtained directly from the two algebraic equations. And this is an explicit approach. Using this approach, the boundary layer properties at grid point, means point I plus 1 and j, are solved explicitly in terms of the known properties at point I and j plus 1. And recently I and j minus 1. When we have theta between 0 and 1, then our functions f appear as unknown. And so we have 6 unknowns and only 2 equations. Therefore, the finite difference forms must be evaluated at all of the grid points through the boundary layer at station I plus 1. And as it should be simultaneous, leading to an implicit formulation for the unknown. In particular, if theta equals 1 over 2, the scheme becomes the well-known Crank-Nicholson implicit procedure. And if theta equals 1, the scheme is called the fully implicit. This implicit scheme results in large system of simultaneous algebraic equations, the coefficients of which constitute block triagonal matrices. And namely, at this stage, return to the original boundary layer equation in physical coordinates. The finite difference schemes already mentioned can be applied directly to this equation. There is no compelling need to deal with the transformed equation. So in this case, we have our first expression here on the middle of this one, and the next one for du over dy. In this case, the real physical variables are the unknown, such as previous u plus 1 and u 1 minus j. However, when the computations are carried out in physical xy space, the grid spacing in the y direction must be very small. This is because the boundary layer properties change rapidly near the wall, and the grid must be fine enough to accurately define these changes. Therefore, the transformations of zeta eta space given in our two equations is still useful here, because the Lee-Doronicin transformation stretches the grid in the normal direction, especially near the wall, I already mentioned. So, therefore, it is frequently recommended to carry out finite difference calculations using the transform zeta eta space. So, in summary, a finite difference solution of a general, non-similar boundary layer proceeds as follows. First, the solution must be started from a given solution at the leading edge, or at a stagnation point. Say you remember the station 1 in the last figure, okay? As stated earlier, this can be obtained from the appropriate self-similar solution. Second, at station 2, the next downstream station, the finite difference procedure reflected by our two equations on the middle yields the solution of the flow field variable across the boundary layer. And third, once the boundary layer profiles of U and T are obtained, the skin friction and heat transfer at the wall are determined by these two equations on the right side of the bottom. So here, the velocity gradient can be obtained from the known profiles of U and T by using one-side differential equation like this one on the bottom. Okay? So, in last two equations, the subscribed 1, 2, and 3, denoted the wall point, and the next two adjacent grid points above the wall. Of course, because of the special boundary conditions of no velocity slip and a fixed wall temperature, so U equals 0, T1 equals TW or T sub wall in this equation. Okay? The preceding steps are repeated for the next downstream location. Say station 3. I remember station 1 on the bottom, 2 and station 3 in this figure. In this fashion, by repeating applications of these steps, the complete boundary layer is computed, marching downstream from a given initial solution. An example of the result obtained from such finite different boundary layer solution is given in this and the next figure. These are calculated for flow over an axisymmetric hyperboloid flying at 20,000 feet per second at the altitude of 100,000 feet with a wall temperature of 1000 Kelvin. At this condition, the boundary layer will involve dissociation and such chemical reaction too. Chemically reacting boundary layers are here. However, some results are presented here just to illustrate the finite difference method. For example, this figure gives the calculated velocity and temperature profiles at a station located at X over Reynolds number 50. Sorry, not Reynolds, radius. So it is a nose radius. We have this one, X over radius over 50. The local values of velocity and temperature at the boundary layer edge are also quoted in this figure. So, considering the surface properties, the variation of CH and CF as functions of distance from the stagnation point are shown namely in this figure, CH and CF. But you should be noted that the following physical trends will illustrate it in this slide. And first, the shear stress is zero at the stagnation point, as is always the case. Then it increases around the node, reaches a maximum, and decreases farther downstream. Second, the values of CH are relatively constant near the node, and then decrease farther downstream. Third, Reynolds analogy can be written as the CH proportional CF over 2S, where S is called the Reynolds analog factor. For the flat plate case, we see S is a Prandtl in power 2/3. However, clearly from the results of this figure, we see that S is a variable in the north region because CH is relatively constant while CF is rapidly increasing. In contrast, for the downstream region, CF and CH are essentially equal. And we can state that Reynolds analogy becomes approximately, in our case, CF over CH, CH over CF equals 1. The point here is that Reynolds analogy is greatly affected by strong pressure gradient in the flow, and hence loses its usefulness as an engineering tool in such cases, at least when CH and CF are based on the free stream quantities as shown in this figure. Okay? I think it's enough for today. And I hope you enjoyed this lecture, and I'm looking forward to seeing you next time. Bye.